Pretend for a moment that you are a second-year medical student and you're in the hospital shadowing a doctor. And the doctor that you're working with today happens to be a cardiologist, and right now he is seeing a patient who is perfectly healthy but wants to have his heart checked out because he's an athlete for his school. And so the doctor decides to order an EKG for this patient just as a baseline. And as a second-year medical student, you're thinking to yourself, this is great, I already know something about EKGs and how they're made. And you remember to yourself that an EKG is made by placing 12 different leads on a patient's skin. There are 6 limb leads and 6 precordial leads, and all an EKG is the voltage tracing from each one of these leads. But now let's say that even though you're a second year, you've never actually looked at a real EKG tracing before. So you're really excited to see this patient's results. And so when the EKG comes back, it looks something like this. And remember, the patient is completely healthy, and so this tracing is actually normal. But you are surprised because you start to take a closer look at the leads and you realize that the voltage tracing from one lead looks different from the voltage tracing from the other leads. So let's say you're looking at the tracing for lead V1. It looks completely different from, say, the tracing from lead 3. You see kind of a waveform that looks like this in lead 3, but you see a waveform that looks like that in V1. So you might be wondering at this point, what do differences like that actually mean clinically? And how can we find patterns in what we are seeing and then use that information to assess whether a person is sick or healthy? And to answer these questions, I'm going to walk you through an example that will help you to think critically about where differences in voltage tracings on EKGs actually come from. And in walking through this example, the hope is that by the end of it, you understand more about why EKG tracings from real patients look the way they do. So let's go back to our precordial leads, which, as I'll remind you, sit like this on a person's chest. And remember that this is the front side of the person's body, and this is the back of the person, and the leads run like this. So here's the question. Pretend that you have a healthy patient. You're looking at the voltage tracing from each of the precordial leads, that is V1 through V6. Out of these 6 different precordial leads, which one is going to have the highest amplitude voltage on the tracing, and which one is going to have the lowest amplitude voltage on the tracing? There's one little bit of information that I should give you before letting you run loose with this question. And that is how charges actually move in a healthy heart. So if we go back to our diagram of the different planes that run through a person's body, in a healthy heart, charge should be moving in a certain direction. In the coronal plane, it would look like this. It would actually run parallel to V2, going from the person's top right of the body to the person's bottom left. That is the healthy way charges move if we were looking just in the coronal plane. But if we were to look in the transverse plane, the charges also kind of move from the front of the person's body to the back. So there's a little bit of backward motion too. It would look something like this. And if you extend the plane, you're going from front to back. So knowing that, and then also knowing how leads work and how the different precordial leads are positioned in the body, you now have all the pieces of the puzzle to answer the question. So as you guys think about this, I'm going to give you a hint, and that is that the precordial leads all lie in the transverse plane. And so what does the motion of charge look like in a healthy person in the transverse plane? Well, I've just answered that question for you. It looks something like this. It's going from the front to the back. And now another question you might be wondering is, does the motion of charge in the coronal plane actually matter? And the answer is actually no, because the coronal plane and the transverse plane are at right angles. So if this were the coronal plane, a square in the plane of the page, then the transverse plane would look something like this. And as you can tell, they're at right angles to each other. And if the motion of charge is at right angles to the plane that you're considering, it's actually not really going to change anything. So knowing that, what would you predict? Well, if you look at the direction of charge motion right here, and then if you compare it to V1, you'll see that they're nearly, at least in this diagram, at 90-degree angles. So for V1, you would expect a baseline voltage. But then you see that this arrow is the most parallel to V6. So then you would imagine that V6 would have a nice, highly positive amplitude. And so given the way this diagram is drawn, you'll see that V2 through V5 will kind of have an intermediate set of voltages in between. So it would look something like this, where V6 has the highest voltage. So the answer to the question is V6 would have the highest amplitude, and V1 would have the lowest amplitude. And this pattern is generally seen in healthy people. There should be an increase in the amplitude of voltage going from V1 to V6. And sometimes the voltage does peak at V4 and V5, and sometimes it does peak at V6, but in general, that's the pattern you're supposed to see. So now that we have the answer, let's see what we would find if we were to go back and look at the tracing we saw in our healthy patient who came into the doctor's office. So here's what his tracing looks like. And again, we're going to look just at the precordial leads, which are here. And we want to see whether we see the same pattern in V1 through V6 as we just decided there would be. So let's look at V1 first. We see here that there is a tiny divot upwards like this, and then there is a big spike downward like this. And so this tiny divot upwards is actually a really, really, really small R wave. And then the deep spike that follows it is the S wave. So the positive deflection we're looking at here is the R wave. Now, if we go to V2, we again see a tiny divot and a big spike downwards. But our tiny divot, the R wave again, is a little bit bigger than it was in V1. And if we go to V3, we see the same pattern again, but here the R wave is a little bit bigger than it was in V2. And so if we keep walking along this set of precordial leads, we see that in V4 the R wave is a little bigger, V5 it's gotten substantially bigger, and then finally in V6 it's the most positive deflection we've seen yet. And so we see that for our healthy patient, the EKG tracing is following exactly the same pattern as we saw here, which is where V6 has the highest deflection and V1 has the lowest or the least positive deflection. And so we can assume that for our patient, the direction of motion of charge in the heart is going to be pretty similar to this pink arrow right here. And that is responsible for making our tracing look like this, at least in the precordial leads.